So hello everyone, I'm Mark Lundstrom and I'd like to welcome you to this course on the essentials of MOSFETs. So as you all know, the transistor is the basic building blocks for all of the electronics that we see in our world today. This is a course about how transistors work. We're beginning in Unit 1 to talk about some fundamentals. We're not going to look inside the transistor very much in this unit. We're going to talk about what happens when we apply voltages to the terminals, what currents do we measure, and just get familiar with transistors in this unit. So we'll begin in Lecture 1 with just basically treating the MOSFET as a black box. But first, a very quick look. This is a cross-sectional cartoon of a MOSFET of maybe a few years ago, but it shows the basic parts. The devices that we will be working with are discussing are fabricated on silicon. This is P-type, positive silicon. This is an N-channel transistor. There's a region that is a source of charge carriers, electrons in this case. There's a region that's a drain. There's a gate in between that controls the flow of electrons between the source and the drain. There's a very thin gate oxide, a gate electrode. If we apply a large enough voltage, we'll turn the transistor on. This is a cross-sectional diagram. If we look at the top of this transistor, this MOSFET, we see the source here, we see the drain on the other end, we see the gate in the middle. The width W here it would be a direction coming out of the page in the cross-section. The current is proportional to the width. If I make the width twice as wide, I'll get twice as much current. So that's what the physical structure looks like. In this unit, we're really not going to be discussing the physical structure. So the first transistors were what we call discrete devices. They were packaged up inside a little package with a few leads, and electronic circuits were assembled by putting these transistors together. It wasn't long before transistors were all integrated into a single slab of silicon, a silicon chip, and wired up together. One of the first was the Intel 4004 microprocessor, which had 2,300 transistors wired up. Today we have billions and billions of these transistors on a chip. This is not a course on integrated circuit technology, but it's a course on how one of those billion transistors actually functions, the physics of those devices. So in this lecture, we're going to think about the transistor as a black box. There's some piece of silicon inside the box that consists of the transistor. We see the wires that come out. Typically, there are 3 leads, sometimes a 4th. There are 2 leads, terminals 1 and 2, through which a large current flows. There is another lead which controls the current through those 2 terminals, and sometimes there's a 4th terminal. There are many different varieties of transistors. We'll be focusing on MOSFETs. There's lots of other types of transistors. We'll be seeing a few of those in the last unit, but our focus is going to be on the MOSFET, a particular type of transistor. But the physical operation of this transistor is very similar to many other types of transistors. So what we'll be learning is applicable to other devices as well. This is the device we would call the bulk silicon MOSFET. This is the way that we will draw this when we're thinking about it just from a circuit picture. We don't want to draw a complicated physical representation of the device. We would draw this circuit symbol. So you can see the source, drain, gate terminals here. Sometimes there's a 4th terminal. We would call that the body in this case. So we'll be drawing transistors this way just so that we don't have to draw the detailed physical structure. Now, I will point out modern transistors have sophisticated structures that look somewhat different. This is a cartoon of a device called a FinFET, which is what the most modern technologies now use. In this case, the transistor itself is built in a thin fin of silicon that sticks up vertically. The gate wraps around. The operating principles of this device are very similar to the classic device we showed earlier. There are reasons that people have gone to this particular structure, and we'll talk about those reasons later on in the course. Okay, but for now, we're just going to talk about, we have a transistor, we have some leads, we apply some voltages, what happens? We're going to try to get familiar with the current voltage characteristics of the transistor. So here's our schematic of a N-channel MOS transistor. We're interested in what current flows when we apply voltages to these 3 terminals. Now, we would like to have an input, and we would like to have an output. We'd like to have 2 input leads, 2 output leads, This is basically a 3-terminal device, so one of the leads needs to do double duty. In this particular configuration, we would call this a common source configuration because the source is one of the input terminals and the source is also one of the output terminals. So that's a common source configuration. Now we can plot the current versus voltage characteristics in a number of different ways, and you'll want to get familiar with these terms: transfer characteristic and output characteristic. So the transfer characteristic is the output current, the drain current flowing into the drain, as a function of the input voltage, the voltage between the gate and the source, at a fixed voltage between the drain and the source. So that's the transfer characteristic, the output current versus the input voltage at a fixed output voltage. We could also plot these characteristics in a different way. We would call them the output characteristics. This is the output current as a function of the output voltage when we fix the input voltage at one particular value. So these are terms we'll use over and over in the course: the transfer characteristic of a transistor or the output characteristic of a transistor. Now we're going to try to understand the IV characteristics of transistors. So to begin with, we can look at the IV characteristics of a very simple device, a resistor. So we know Ohm's law says that current is voltage divided by resistance. If we plot the IV characteristics, the current through this resistor as a function of the voltage between its two terminals, it's just a straight line. I is equal to V over R. If we have more resistance, we get less current. If we have less resistance, we get more current. So that's the IV characteristic of a very simple device, a resistor. We're trying to understand in this lecture the IV characteristics of transistors. Now, another device that we talk about, we frequently will introduce in a beginning electrical engineering course, is something that we call an ideal current source. Of course, they don't exist in practice, but we can make some pretty good current sources that look close to this. The property of an ideal current source is that it delivers a specific current, I0 in this case, no matter what voltage we put across its two terminals. So when we plot its IV characteristics, we get the current I0 independent of the voltage that's across the two terminals. That's our definition of an ideal current source. Now, we're interested in understanding the IV characteristics of transistors, of the MOSFET specifically. And the transistor characteristics will all look something like this. If we apply a small voltage between the drain and the source, the IV characteristic will look like a resistor, just a linear straight line. If we apply a large enough voltage between the drain and the source, the IV characteristic will begin to look like an ideal current source. The current will saturate and will be independent of the voltage that we apply, as long as the voltage is big enough. So that's the basic IV characteristic of a transistor. There is this small voltage regime, small voltage between the drain and the source, in which the device operates as a gate voltage controlled resistor. If we change the gate voltage, we'll change the slope here. And there is this saturation regime where the device operates as a gate voltage dependent current source, but the current is independent of the voltage between the drain and the source terminals. So these are the general IV characteristics of a transistor. We should make them just a little more realistic. Ideal current sources don't occur in practice. In practice, what we would usually see, if we apply a little more voltage, we get a little more current. If we apply a little less voltage, we get a little less current. The current source is not quite ideal. We think about that by modeling it by putting an ideal current source in parallel with a resistor. So the larger the voltage, the more current flows around the resistor, and we get a little more current. So a real current source will always have a finite resistance. It won't be ideal. Now, similarly, transistors don't behave as ideal current sources with a large voltage between the drain and the source. They'll behave like a current source with some output resistance. There'll be some slope to that output characteristic. Hopefully in a good transistor, that slope will not be very large. The device will more or less saturate and the current will be more or less constant if the voltage is large enough between the two terminals. But the real device will have some output resistance. Now, the way you will usually see transistor characteristics plotted, if we plot the output characteristic, that is the output current versus the output voltage, the drain and the source are the two output terminals, we would get a set of characteristics that look like this. Each one of these lines here is at a different input voltage, the voltage between the gate and the source. So as we increase the input voltage, we get another characteristic. Each one of those characteristics has a region where the device operates as a resistor and a region where it's trying to operate as an ideal current source, but it has some finite output resistance. So these are the classic IV characteristics of transistors, and these IV characteristics make transistors useful in circuits. You can see here the linear region and the saturation region. One thing you're going to want to get used to now in this lecture and in this unit is there's a bunch of terminology that we're going to be using throughout the course, and this is an opportunity to get familiar with this terminology. We'll frequently be trying to understand the transistor in the linear region. We'll be trying to understand the transistor in the saturated region, and this figure here illustrates what we mean by those two regions. There is a critical voltage, and it's kind of, not precisely defined, but you can see here that there is some voltage. We call this VD-sat, the drain saturation voltage. If the voltage on the drain is bigger than that, we're in the saturation region. If the voltage is less than VD-sat, we're in the linear region. Okay, now there's also another region that is hard to see here called the subthreshold region. So if the gate voltage is not big enough to turn the device on, then essentially no current flows. And I'm down here at ID equals 0. So the gate voltage has to be big enough, then we start to see current flowing. We make it bigger, we see more current. We make it bigger, we see more current. Each value of the gate to source voltage gives us a different line on this output characteristic. Okay, I also mentioned earlier there's this transfer characteristic. We will frequently be looking at the transfer characteristics. So here's our output characteristic again. Here's our VD-sat, which is the borderline between the saturation region and the linear region. Now I could go and I could plot the IV characteristics in a different way. I could fix the drain voltage at a low value, and then I could sweep the gate voltage. Then I would be plotting a transfer characteristic, the output current versus the input voltage at a low voltage applied between the drain and the source. I could also do my transfer characteristic by applying a high voltage between the drain and the source, and then sweeping the gate voltage to higher and higher values and plotting the drain current that results. So if I were to do that, I would have a plot of output current versus input voltage. If I had a fixed low voltage between the drain and the source, I might get something like this. If I had a high voltage between the drain and the source, I would get more current, and I would have something like this. And you can see that there's a transition. Essentially no current flows until I apply a big enough voltage on the gate, and then current begins to flow. So that's another term that you'll want to get familiar with. That's the threshold voltage of the transistor. We need to apply a voltage larger than the threshold voltage in order for significant current to flow. Okay, so output characteristics, transfer characteristics. Spend a little bit of time to make sure that you're comfortable with what we mean when we refer to these two different types of characteristics. Now, we're going to be talking about different applications of transistors. We're primarily focused on the physics of the transistor, but in order to understand what's important for applications, we need to know a little bit about how transistors are used in applications. There are two general ways that we can use them. We can use it as a digital switch, which is either on or off. We can use it as an analog device, which takes a small time-varying signal coming in and produces a large time-varying signal, an amplification of that signal. So digital versus analog, transistors are used in both applications, and one of the first things we want to do is understand what type of IV characteristics are useful and important for digital applications, what types of characteristics or device parameters are useful for analog applications. I will also mention that there are two different flavors of transistors. I've been talking about an N-channel transistor. N for negative, it means the charge carriers are negatively charged electrons that are flowing from the source, which is a source of electrons, out to the drain, where they flow out through the terminals. And in order to have the current flow, we have to apply a voltage on the gate that is more positive than this threshold voltage. Now, the modern mainstream electronic technology these days is CMOS technology. CMOS is complementary metal oxide semiconductor technology. There is a complementary device then, and that complementary device would be built on an N-type substrate, negative. It would have a source of positive charge carriers, holes. It would have a drain, also where the positive charge carriers go out, and it would have a channel. And in order for the channel to connect the source to the drain, the voltage on the gate would have to be more negative than the threshold voltage. The threshold voltage would be a negative value. The gate voltage would have to be more negative than that. You can remember the sign because negative gate voltage would attract holes and create this P-type channel. The holes would then flow from the source to the drain and out to terminal, and current would flow out. In the N-channel device, electrons flow from the source to the drain. Negatively charged electrons flow out, which means current flows in. So mainstream technology is CMOS technology, and the C stands for complementary. There is always an N-channel device paired with a P-channel device. Okay, so we have talked about a lot of things in this lecture, and so let me just summarize the key takeaways that you should be familiar with. First of all, transistors are basically three-terminal devices. Sometimes there's a fourth terminal that plays a role too, but they're basically three-terminal devices. One of the terminals, the control terminal, controls a large current through the other two terminals. Sometimes it's a small input current that does the control. In the MOSFET, it's a small voltage that does this control. Transistors can operate either as a voltage-controlled resistor, when we apply a small voltage between the two main terminals, the drain and the source, or they can operate as voltage-controlled current sources, when we apply a large voltage between the drain and the source. And we talked about the different ways of plotting these characteristics, output characteristics, and transfer characteristics. Now, the particular shape of the IV characteristics that I've illustrated in this lecture make them useful for both digital and analog circuits. So what we're trying to get comfortable with in Unit 1 is understanding some terminology in the shape of these IV characteristics. The shape of the IV characteristics and the magnitude of the current is all controlled by the physics of what's going on inside the transistor. That's the real focus of this course, and that's what we're going to be discussing in more detail in Units 2, 3, 4, and 5. Okay. All right, so that's it for Lecture 1. Now, in the next lecture, we're going to move on to a topic. We're going to get ready to discuss the topic of device metrics. So device engineers will do a few quick measurements on a transistor to determine whether this transistor is a good device for digital applications or for analog applications. Now, in order to understand what these simple device metrics are, we need to know a little bit about what makes how digital circuits operate, how analog circuits operate. So digital circuits is the subject of the next lecture. And the lecture after that, we'll continue with a quick discussion of analog circuits.